Today, we want to discuss about the optimizations for functions with several variables. For introduction, optimization is usually used for problem solving about the underlying situation. The examples for common application which involves optimization problems are minimal cost, maximal profit, and optimal designs. For history, Lagrange found a clear way to express all the conditions into a single equation which has wrote down a specific new function which takes in all the input variables, and he also emphasized the importance of his multipliers for constraints optimization. However, von Train didn't find out the Maximus principle. Finally, the complete formulations of PDE constraints optimizations was introduced by Lyons. Furthermore, for solving the question which related to optimization for functions with several variables, the differential calculus is included in solving process. The PDE is used in the techniques of Lagrange multiplier. In conclusions, optimization problems is widely applied in many areas, and the use of suitable optimization methods will make decision makers able to save more time to find the best solution.
So I'm going to present about a key concept. Every decision maker always wishes to find an alternative with the most cost-effective or higher achievable performance under the given constraints. In instance, maximization means striving to attain the highest or maximum result or outcome. And furthermore, the meaning of optimization problem is maximizing or minimizing some function which is relative to some set. So always represent a range of choices available in a certain situation. So we are going to find the best function with the comparison. So optimization problems have three fundamental elements, which are objective function, collective of variables, and set of constraints. Therefore, the objective of this study is to determine the optimum value of a multivariable function with a given constraints. Large-range multiplier will be the main.
In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function fxy subject to the constraint gxy. The extreme values of fxy is when there is a point is restricted to lie on the curve gxy equals to k. We will illustrate the problem by defining a function fxy equal to c while c equals to any real number. The figure below shows several level curves of f with the graph gxy. We want to find the largest value of c which the graph fxy equal to c intersects with the graph gxy equals to k. From the figure, this happens when the graph of fxy touches the graph gxy at the point x0, y0. In this case, this will maximize fxy subject to the constraint gxy equals to k. Both graphs touches each other will have a common tangent line, so the gradient vectors are parallel, and this equation is formed for some scalar lambda, where g x0 y0 is not equals to 0. The constant lambda is called the Lagrange multiplier. For function of two variables, we will look for the extreme values of fxy subject to the constraint gxy equals to k, which are the values of xy and lambda such that the equation above will be written in terms of components by using partial derivatives, which become. From this situation, these three equations is with three unknowns x, y, and lambda, but it is not required to find the explicit value of lambda. From the results, evaluating f at all points x, y, the largest of these values is the maximum value of f, and the smallest is the minimum value of f. Next, I will talk about second derivative test. The maximum and minimum of f can be determined by using second derivative test. The formula are as below, where AB is the optimum point found with Lagrange multiplier method, and the result and interpretation are shown in the table next slide.
In this study, the first application conducted is related to the utility of economics. Briefly explained, this example is explaining that a society which obtains a limited funds of $400 from outsider willing to purchase some bonds and barter for their daily use. According to the question, the important data is a utility function, the price, the budget functions, and the current allocations. For question 1, a comparison has been made after the derivative and substituting the current conditions 3 Ux equals to 2 and Uy equals to 3. Then divide by its respective price, we found out that the bonds ratio is 0.02 while the barter ratio is 0.06. From this, we can conclude that barter has a higher marginal utility to price ratio compared to the bonds. For question 2, by referring to the line graph, there are various types of allocation with a distinct utility but same budget can be made. In short, the table shows the detail. For this question, the point choosing is 2.5 and 3. From this, it demonstrates an improvement of utility in which the utility increased from 6 to 7.5. As a result, the society will choose to buy the item with a higher marginal utility to price ratio in which more barter but less bond have been purchased. Moving forward is about question 3. Lagrange multiplier has been applied to find the optimizations of allocations. First, we let f equals to the utility function and g equals to the constraint function. By substituting the function into the formula, a new function has been developed. Then, find the first and second derivative of the function. Then, we let fx equals to fy equals to f lambda equals to 0. By using the simultaneous equation, it found out that y equals to 2x. After plugging it into the equation 3, the critical point 2, 4 can be discovered. Further, to determine whether the critical point is a local maximum or not, D has been found. Since D is negative, 2, 4 is currently a saddle point.
And for the second application is about the electric circuit. Electricity prefers to flow in the way that minimizes energy loss to resistance. Hence, this report wants to determine how to minimize energy loss in a parallel circuit. According to the question, the important data is the energy loss function, the constraint, the resistance value, and the total current. To find the minimal energy loss, we also use Lagrange multiplier method. Firstly, we will find a new equation by using energy loss function and constraint function with Lagrange multiplier lambda. Then, we will find the first derivative and second derivative of the function. We set the first two equations to 0 and then we solve for lambda. Then, we will find the values of I1 in terms of I2 to solve the equation for delta C over delta lambda. Then, we set delta C over delta lambda equals to 0 and we substitute the I1 value just now to find the value of I2 and also the I1. What will we get? We obtain a current divider rule. Substituting the current and the resistance value, and we will find that it shows the minimum energy loss. And also, we apply second derivative test. The second derivative and the D are positive. Hence, it is proof that the result will be the minimum energy loss. Throughout the report, two applications of partial derivative have been discussed in economics and engineering. As a decision maker, it is imperative to apply the most relevant and suitable technique to tackle different problems respectively. Lagrange multiplier has played an important role in the determination of optimal value with the objective function and the constraint function. Optimization method is asserted to be an assistant tool which helps to save the cost, time, and energy